what could be your observation? In case of negative clamper, the output waveform is going to get shifted in the downward direction by minus Vm level. So that is the difference. And you can also derive a special note on practical diode analysis. So this is basically ideal diode analysis because we did not consider the effect of Vk. In case of, if you consider practical diode, what is going to happen is that the charging voltage Vc, in case of ideal diode, what is the charging voltage Vc? The charging voltage Vc is nothing but Vm, right? In case of practical diode, the barrier potential will limit the charging voltage to Vm minus Vk value. So you have to bring it Vk into the picture. So the charging voltage is not Vm, instead it is Vm minus Vk. Okay. And similarly, during the output analysis, this equation you will end up in getting, right? V0 is equal to Vi plus Vc, right? So in case of practical diode, it is nothing but Vi plus Vc. And what is Vc? Vc is Vm minus Vk. So the barrier potential you need to consider into the equation, and due to which what happens is that we can make a similar table here. This is Vi, this is V0, this is for positive half cycle, and this is for negative half cycle. Okay, so when your input is 0, output going to be 0 plus Vm minus Vk. So it is Vm minus Vk. Okay. On the other hand, when your input reaches positive maximum, the value of the output going to be Vm plus Vm minus Vk. So what you have to understand is that everywhere the output is getting limited by a factor of Vk volts. So Vk is basically limiting the output. So your overall output when Vi is equal to plus Vm going to be 2 Vm, which is the ideal case, minus Vk. Okay. And for negative half cycle, same analogy can apply. When your negative half cycle starts from 0 volts, output going to be Vm minus Vk. On the other hand, when your negative half cycle reaches negative maximum, which is nothing but minus Vm, your output going to be at minus Vm plus Vm minus Vk, which is equal to minus Vk. And you can plot the input-output waveforms. Let's say this is your input, white is your input, and say yellow waveform is your output. Okay. So for practical diode analysis, when your input is 0, output is at Vm minus Vk level. So this is your input. So when your input is 0, output is Vm minus Vk. That means to say somewhere here. Okay. And when your input reaches plus Vm, output will be 2. So 2 Vm minus Vk. And once again, when the input falls to 0, that is at this point, output will be at this point. Okay, and then you can complete the positive half cycle. So this is your positive half cycle. And for negative half cycle, when your input is 0, output is at Vm minus Vk level, that is this point only. And when your input reaches minus Vm, okay, when your input reaches minus Vm, where will be your output? Output will be at minus Vk. In case of ideal diode, your output was at 0 volt level, but in case of a practical diode, in a positive clamper, you will find the negative peak of the output at minus Vk level. Minus Vk level going to be somewhere here. So a small portion of the negative half cycle of the output, leaks into the downward region. So this is your, positive clamper analysis. Okay. So negative clamper analysis, I will leave it to you. So all what you have to do is you have to apply the complementary analysis logic. So I'll draw the circuit and I'll give the hint. Negative clamper. Okay. So the circuit remains the same. A source, a capacitor, and comes the diode. So to distinguish between positive and negative clamper, all what you have to do is you have to swap the diode terminals. So in case of negative clamper, upper side will have an anode terminal and the lower side will have a cathode terminal. Alright, and then comes the load. And then you have to identify the charging cycle. Pretty easy to identify charging cycle. So how do you identify the charging cycle? You should identify the charging cycle in such a way that that particular charging cycle will forward biases the diode. So for example, if you consider upper side positive and lower side negative, you can clearly observe that negative terminal of the source is connected to cathode terminal. So the charging cycle is going to be the very first positive half cycle of Vi. Very first positive half cycle of Vi. So what it will do? Vi will forward biases the diode. So you can say Vi forward biases the diode, and diode acts like a closed switch. Acts like a closed switch. So we can do the changes here itself. It acts like a closed switch. So you can just close the contacts here. Right. And obviously across a closed circuit, the voltage becomes 0. So if we measure the output voltage across R, you will get it as 0. So during charging cycle, the output voltage always remains 0, whether it is a positive clamper or a negative clamper. Okay, all right. And then you have to assign the polarity for the capacitor voltage. So the terminal which is connected to a positive terminal of the battery attains positive polarity, and the opposite side attains negative polarity. Now you can apply KVL. So apply KVL in clockwise direction because we are considering positive half cycle, right? For negative half cycle, we would have taken it in anti-clockwise direction. So in clockwise direction, when you apply KVL, you will get Vi minus to plus, then you have plus to minus, minus Vc, right? Then you have plus to minus, minus V0 is equal to 0, and note that output voltage is 0. So the capacitor voltage Vc is equal to Vi, and therefore when the input reaches Vm in the positive half cycle, the capacitor gets charged to Vm. Right, just like your positive clamper, even in a negative clamper, you would see that the capacitor gets charged to maximum value of the input voltage. Okay, and if you use a practical diode, then Vc going to be Vm minus Vk. So you have to just bring in, Vk into the picture. Okay, once the capacitor is charged to Vm, you can proceed to find the output analysis. Okay, output analysis, as I said, just consider positive half cycle, and for negative half cycle you can just provide the complementary explanation. So output analysis. So first draw the circuit in as it is formed. This is V naught, right? So this is Vi. So for output analysis, first let us consider positive half cycle. You can even consider negative half cycle, but positive half cycle generally, works in an easy way. So plus minus, and you should copy and paste the polarities. So for a negative clamper, this is how the capacitor was charged. Left hand side was positive and right hand side was negative. Okay. And you can observe that during positive half cycle, the diode is kept in off state. Okay. Many of you may raise the eyebrows, on what basis I said the diode is kept in off state. Okay. So remember one thing, Vi is your AC source, right? So AC source can have different instantaneous values. And together with this AC source, you have a capacitor, and the capacitor is modeled as a DC source, because once the capacitor is charged to plus Vm volts, it is not going to discharge because of the very high time constant. That is, product RC is quite large. Okay. Now, if let's say Vi is less than Vm, or Vi is equal to Vm, okay, input can be less than Vm because there can be instantaneous values which can be less than the maximum values, or at the maximum input can be equal to Vm, right? But input can never be greater than Vm, because Vm is one of the unique instantaneous value of the input itself, right? So if it could be Vi less than Vm or Vi is equal to Vm. For both the cases, the diode D is maintained in off state. Okay, so this is one of the beautiful concept in clampers, that once the capacitor is charged, okay, the diode will not be in conduction. Okay, in the output analysis, whether you consider positive half cycle of the input or negative half cycle of the input, the source and the capacitor, they work in such a way that they always keep the diode in off state. Okay, so the diode will never conduct when you move towards the output analysis. So diode, you can blindly keep it in off state. Okay, that's because of the following mentioned reason. Alright, so diode is in off state, so you can redraw the circuit, plus minus. So this is your capacitor voltage, plus minus. This is your instantaneous half cycle of the input. And this is where you observe your output. So you can apply KVL. So what do you get? Vi minus Vm minus V naught is equal to 0, or V naught is equal to Vi minus Vm. So this is your output equation. Now using this output equation, you can determine the status of the negative half cycle of the output as well. Okay. So the same equation can be used to determine the status of the negative half cycle of the output. Okay. So you make a small table here. So this is your input and this is your output, and you want to find the output for positive half cycle as well as negative half cycle, right? So first you write positive half cycle, and here itself you can write negative half cycle. Okay, so when your input is at 0 volt, okay, in the positive half cycle, your output will be at 0 minus Vm is equal to minus Vm volts. right? On the other hand, when your input rises to positive maximum Vm, okay, your output becomes, sorry, Vi. Okay, so what is the value of Vi? Vi value is Vm minus Vm, which is equal to 0. Okay, so that's the status of positive half cycle of the, output. And let us see what will happen to the output when we consider negative half cycle of the input. Okay, so in the negative half cycle, when your input is 0, we will roll back to this particular case. So it is 0 minus Vm, which is equal to minus Vm. On the other hand, when your input reaches the negative maximum, that is when your Vi becomes Vm in the negative direction, so negative direction is incorporated with negative sign here. So what happens to your output? Output is Vi minus Vm. And what is Vi? Vi is minus Vm, which is equal to minus 2. Okay. So, alright, so let us pictorially represent the solution of this equation in a graph. Right? So this is your voltage axis. Okay, first let us draw the input Vi and let us also draw the output. Okay. So when your input is 0, output is at minus Vm level, right? So minus Vm is somewhere here. Done. And when your input reaches plus Vm for the positive half cycle, your output reaches 0 volt. And once again, when your input reaches 0 volt, output stays at minus Vm volt. So you can draw the waveform. So this is your positive half cycle of the output waveform. Okay. Now let us look at the negative half cycle. So when your input is 0, output is at minus Vm. On the other hand, when your input reaches minus Vm, your output reaches minus 2 Vm. And similarly, when your input reaches zero volt, output will be at minus Vm. So complete the cycle. So as you can clearly observe that the wave is getting pushed in the downward direction by what amount? By negative Vm volts. Since the waveform is getting pushed in the downward direction by negative Vm volts, it is called as a negative clamper. So you can see a downward shift. Downward shift, right? So this downward shift is attributed to negative clamping action. And that's why it is called as a negative clamper. Okay, so negative clamper with practical diode analysis is pretty simple. The charging voltage of practical diode. Okay, if you consider with a practical diode, the following changes you need to bring in. So capacitor Vc is not just Vm, instead Vm minus Vk, and your output voltage V0 is, this is what I wanted to point out. So output voltage V0, what did you get? Vi minus Vm, right? So Vi minus Vm minus Vk. This you have to bring in, okay? And once you bring in this Vk, you'll be able to proceed. Okay, so please try it out with a practical diode as well. I have written the equation. Try completing the waveforms, and also you can experiment with introducing a battery into the clamper circuit. So if you introduce a battery into the clamper circuit, it is called as a biased clamper. So you can have a biased positive clamper as well as you can have a biased negative clamper. So these biased clampers are used to take control of the DC shift. Okay. So if you do not want to add a VM level of DC shift, then you can use a biased clamper. So for example, let's say your amplitude of the input, okay, let's say max value, which is nothing but Vm of Vi is 5 volts. Okay, so in case of ideal clamper, if you calculate Vc, you will get Vc is equal to Vm. And what's the value of Vm? Vm is 5 volts. So the capacitor is going to get charged to 5 volts. On the other hand, if you consider a practical diode, so Vc going to be Vm minus Vk. So Vc is nothing but 5 minus 0.7 for silicon diode. Vk is 0.7 for silicon diode. That is 4.3 volts. So for a practical diode, the capacitor will not get charged to positive maximum. Instead, it is going to get charged to a value slightly less than positive maximum. That is 4.3 volts. And if you don't want to insert 4.3, for instance, you want to insert, let's say, 2 volt. Okay. Say you want to shift the input waveform by, let's say, plus 2 volts. Instead of plus 5 volts, you want to shift the waveform by plus 2 volts. So you have to use an additional source. So that will be, able to subtract this, 5 volts and gives a resultant voltage of 2 volts. So probably, you have to use DC additional source of 3 volts in such a way that the shift 2 volts you will get. So 5 minus 3, if you do, you'll be able to get 2 volts. So you have to place this VR, appropriately, so that subtraction of 5 volts and 3 volts takes place. So subtraction of if 5 volts and 3 volts, if it takes place, then the resultant shift you are going to get it as 2 volts. So such a circuit is called as a biased clamper circuit. Okay, so you can refer to Robert Boylested book for bias clamper examples. Okay.